since 2023, she's fellow from of the American Physical Society, and also she's editor-in-chief of JOSA B. So thank you very much, Irina.
Thank you. I want to use this occasion to thank the organizer for inviting me here. It's a fantastic event. I absolutely love being here, and I really want to talk to more students here. I had a lot of fun during the poster session yesterday, and I love to talk to you guys. So if you see me standing, just come and chat with me. All right, so in this talk, I will be mostly talking about what our group does, specifically to how we apply quantum sensors to different fun situations. But first, I don't know if William and Mary is so famous here, but this is historically the second oldest university in the United States. It was founded in 1693. And we have like 4 presidents graduating, so a long time ago. So, but we have a PhD program. So I know a lot of you are PhD students. You know, if you're looking for the postdoc, give me a call. Or if you know undergrads who would like to come and get the degree in William and Mary, we're always looking for the good students. We actually have a pretty strong representation for atomic physics, both theoretical and experimental. We do have one person working with cold atoms, Seth Obin. You have people working with hot atoms and with the quantum materials. And again, we have actually 2 new theorists who love to do all sort of quantum. From what they're doing, I think it should be cold atoms. So anyway, so if you're interested, let me know. Or if you're in the vicinity, we're not very far from DC, give me a call and come to visit. It would be fun. And as Raul said, I'm also an editor-in-chief on JOSA B, and I've been in the Optica publishing group for a long time. So I know publishing papers look sometimes like a black box, and you don't know what's happening and what should happen. So if you have any questions about the process, feel free to ask me. If you have a nice paper to put in JOSA B, please submit. It's actually a very nice journal. I absolutely love it because it has excellent reviewers. I know not everybody is happy with the reviewers all the time, but it's high quality reviews. And hopefully at the end, you find it useful. And it's a lot of care going to every paper. So think about us. But if you're interested to know also how to get involved a little more with the reviews, again, that's probably more for more senior graduate students who have some experience. There is a reviewer training course which you can take to become a reviewer. If you, at some point, become so proficient with the reviews that you actually want to take a next step and get involved into editorial processes, we have the assistant editor program when you can become kind of an apprentice for the editor and then hopefully get promoted to the actual editor. And then you will be the one making decisions. And then you will know that actually reviewers are not that bad. So, all right, anyway. All right, so what I'm going to talk about today is a little bit about quantum sensors, and specifically kind of 2 generations of quantum sensors. One, how we can use kind of atomic coherent effects to measure in various things. One of them is magnetic field. If you've been in my lecture, you already got that I'm kind of like measuring magnetic field. But also we're doing a lot of fun stuff with electric field recently, so I'm going to tell you about this and how we try to apply it for sensing stuff in the other fields. And then I will talk a little bit about quantum enhancement, more specifically squeezed light, and even more specifically how we can use hot atoms to produce squeezed light. Okay? All right. So there is a big discussion what is quantum sensor. So if you ever want create some activity and excitement in a group of quantum physicists, just come and say, what is really quantum sensor is? And I guarantee the next 15 minutes there will be big discussion of what is quantum and what is not quantum and so on. But here, if kind of definition I take, it's pretty inclusive that if you basically use some sort of quantum coherence interference, that's all quantum sensors. So, and of course, we have a lot of different systems where we reach the regime where you can use the quantum properties to extract some useful information. So this is like a big list here. And I think in general, we can divide the quantum effects into 2 broad categories. So quantum 1.0 is when we're using the quantum states and we're using the quantum things, but this is something which already kind of occurs. So for example, atom is obviously quantum object. And anything associated with quantum coherences is a quantum thing. But you can say that in some of the cases, you don't need you can't describe it classically or approximate classically. So this is our first generation of quantum sensors. And this is actually what used in a lot of sensors already. So we have this in. And then, of course, oops, sorry. So, and then, of course, there is a second generation when we're really trying to use kind of the macroscopic effects, like entanglement on the spin squeezing, where you entangle the quantum properties of multiple things. If you want to entertain one of those is spin squeezing, one of those is entanglement, you figure out which one. That's the AI versions of this effect. Now, you may think, and a lot of people think, that the atoms which are kind of moving around and zipping around and colliding and doing as not a great quantum things. And you will be right, a lot of people think that. Now, I don't know if this movie is popular. It's one of the classic Marilyn Monroe movie. I don't know, who knows Some Like It Hot? Okay, one person, okay. But, okay, in this, you should watch it. It's really fun. It's an old movie, but it's really fun. But in the very end, there is in the movie, one of the guys is hiding as a girl. And the old gentleman over there like really got in love with her, him, her. And at the end of the movie, basically say, okay, we're going to get married. And the guy's like, well, I cannot have children. Like, never mind. And I spend a lot of time with other men. Like, never mind. And at the end, like, I am a guy. And said, well, everybody has some, and nobody's perfect. So I sometimes feel like this when you talk to somebody about quantum sensors. Like, well, but the atoms are moving. Like, never mind. And resonances are broadened, like, never mind. And sometimes there are other things, like, well, nobody's perfect. So that's where the title of my, kind of subtitle of my talk came from. So for those of you who will be on the lectures tomorrow, we're going to talk about how we can use the 3-photon system to get a good access to like a quantumly robust states for measuring. But in general, we're going to use various coherences. Does this thing work? Yes. So we either going to try to access the spin coherences to measure in magnetic field, and we can use either hyperfine or Zeeman state, depending on what we want to do, or we can use the ladder scheme when we basically make a connection between the ground state and excited states. The point of all of those schemes is that we're trying to avoid having atoms in the intermediate state because it's a lossy state, and we don't like losses. And as I said, these sensors, based on all these effects, they already exist, and in a sense, some of them are even commercial. So for example, the atomic clocks, so when you stabilize the frequency source on hyperfine transition in atoms, you can, in principle, buy those. Same things with the various versions of magnetometers, if you can go and buy them. Rydberg sensors, they are kind of stepping into market. I don't think they're as kind of robust product as others, but they're certainly getting there, and I think in a few years we'll definitely see them on the market. And there are other things where people are trying to use, for example, the accelerometers on gyroscopes, which are based on atomic systems in the future. I think these are a few years behind, but again, the progress is relatively fast. So I will illustrate, because I will try to put a lot in the slide, so I have to move fast. But the very general idea of how do we do measurements, as we discussed this morning, you want to find kind of narrow resonance, and then you want to trace the position of this resonance to measure magnetic field. So the resonance I like to use, this is called electromagnetically induced transparency. So essentially, you have the two optical fields, and you create a lambda link which connects these two states together. Now, if the frequency difference between the optical field matches exactly the hyperfine splitting or like ground state splitting of these two states, you have so-called dark state. And at this particular frequency, you will have the reduction of absorption. But it's because we put the atoms in kind of coherent superposition, it's very sensitive to the tunings. So as soon as your frequency deviates, you go back to like a normal absorption, and therefore you can create a narrow peak where you can measure what the frequency of this is. So that means that if your levels move, if you basically lock you lock yourself on the top of your transparency peak and you see how much the frequency changes, you will know what the things are. This is kind of the principle for the atomic clock. They pick the magnetic field insensitive transition. That's how it works. So for the magnetometry, things are a little more complicated. So this is the rubidium-87 level scheme. And now if you shine the light on it, these are all the transitions you can excite. And if it looks like a mess, don't worry about that. But what it means is that depending on what polarizations of your light is, you can excite all these transitions. And if there is a magnetic field, then all the levels move differently. And you basically have, instead of one transition peak, you can have 7 different transition peaks. The nice thing, they're all separated by basically Larmor frequency. So by picking a frequency of 1 peak, the kind of second one, which is separated by the 2 Larmor frequency, or -2. These are kind of our favorite because they survive for all the polarizations. You can basically very nicely measure the magnetic field this way. Moreover, if you actually design your experiment cleverly and you can jump from one to another, you can protect yourself from a lot of systematic shifts, like, for example, light shifts, because it's the same for the same transition. So if you're only looking at the difference, you're immune to, it's at some level of accuracy, to all this transition. Now, this type of magnetometer has been known for a very long time. So what is our group is kind of bringing into the table is that in addition to measuring the magnetic field direction, we also want to look at magnetic field magnitude. We also want to look at magnetic field direction, which is not kind of obvious from here. And you can kind of guess from this messy picture, the way we're going to get information is to take advantage of the difference in selection rules for different polarizations. So for example, if we're shining the light and we rotate the polarization of the light, or we change the direction of the magnetic field with respect to the light propagation and polarization, we're going to always have the same 7 resonances, but the amplitudes of this resonance are going to change. So for example, this cartoon you can see here is basically we're going through all the different directions of the magnetic field. So moreover, it's, the amplitude distribution is kind of like a fingerprints for each of the angles. So we can actually look at them and find which one, which distribution corresponds to this, to which angle. And this is kind of the most recent stuff we get. I know some of the people work here with the vector beams. So one of the things we can do is to use, so in original experiments which we published, we actually rotated the polarization of light and we were looking at the distribution at different points. But for practical applications, having the rotating polarization is not so much fun. So the new things we're trying right now is to using the vector beam. So basically when you send the light in and you have all the polarization already in your beam, so if you pick up your beam with a camera, you can see the distribution for different angles, and then you can analyze it and extract the information about, for example, the direction of magnetic field. So this little cartoon is when my students was rotating the magnetic field direction, and you can see how the position of the maxima rotates, and they will indicate what kind of field you have, and then we can analyze the overall intensity distribution to get the direction. So this is kind of our approach of getting the information about magnetic field. Okay, but you can say magnetometers, everybody's doing magnetometers. The best sensitivity for magnetic field we got was about 2 picotesla per square root hertz. Now, this is actually nothing to be really proud of because the best atomic magnetometers, they can do below femtotesla. So this is 3 orders of magnitude. The advantage of our system, though, is that we can measure, so first of all, it's all optical. There is no RF field or anything involved. And also, we can actually work with a strong magnetic field. So this sensitivity is at the Earth-like magnetic field levels. So this is, again, for those of you who are in the class, sensitivity is good, but sometimes you need to kind of balance it with the other parameters which we can have. Okay. So, but more stuff, which I think for me right now it's more exciting. So how we can use these atomic sensors for something useful, maybe? So a lot of effort for the atomic magnetometry goes into biomedical research when people are trying to measure how the heart works or the brain works and so on. So, and again, this is very interesting, but we don't have medical school, but we have a particle accelerator next to it. So if you have friends who are in high energy physics, we have actually Jefferson Lab National Accelerator Facility like 20 minutes away from us, which I think for our students is fantastic. So they can basically go and work there. But what people there do, they have charged particle beams, and they need to characterize them. So one of the things they ask us when we start talking about our capabilities, can you help us to figure out what magnetic field is, because what the beams are? Because of course it's a vacuum, so it's a complicated system and so on. So currently, one of the best ways people are kind of monitoring their beams is that they literally move the wire across the electron beam and measure the current. It works really well, it's very reliable. But first of all, you cannot do it with the really powerful beams because the electron is going to burn your wire. And else it takes a long time. They have to stop the experiment, they put the wire in, make a measurement. It's like an hour of measurements. They would prefer something faster. So what we decided to try is to say, okay, if we have atoms and we know how to measure, how to use atom to measure magnetic and then electric field, maybe if we add a little bit of atoms kind of in the area around the beam, and then we can measure what magnetic and electric field this atom see, we can recreate what electric and magnetic field the electrons create, and therefore produce the shape and the strength of the electron beam. So this is kind of our general idea. And it actually works pretty well. We have now 2 prototypes. One of them is based on magnetic measurements. And in this case, again, we have a kind of imagine the wire of electron beam. So that's the current. So it's create the magnetic field around this. Now, I'm not going to give a lot of details, but one of the consequences of sending linear polarized light interacting with 2 Zeeman sublevels is that refractive index for 2 will be different, and it will produce the polarization rotation. So at the end, if you send a linear polarized light, it goes through, and depending on the magnetic field, it will rotate one way or another way. Because the magnetic field is kind of circulating, and we're mostly sensitive to the longitudinal magnetic field, kind of above the center of the beam will rotate one way, and below the center of the beam, it will rotate the other way. So this is exactly what we see here. So this is just like the general beam. You can see how big it is. But if we measure the polarization rotation, you can see that in one part of the beam, it's positive, and one part of the beam is negative. And this is and the boundary is exactly where the beam is. And of course, by analyzing the intensity, we can actually recreate where the electron beam is and how broad it is, and how much current we send in. So this is our magnetic field measurement device. And we can check that if we displace electron beam, we can kind of see where the boundary is moving. So for one of them is, it's hard to aim. One of them is here, and then we move it over here. Now, the signal to noise is not great right now. And this is kind of limits how accurate this method is going to be. But my students is working right now on introducing squeezing into this experiment and trying to enhance the performance even more. So another methods we're applying is using the Rydberg atoms. As we mentioned earlier today, Rydberg atoms are very sensitive to electric field. So now we can basically do the same experiment, but looking at how the Rydberg atoms affect the transmission. We're using EIT again. Now this is a ladder scheme. And if you have no electric field, basically all of the J levels of the excited states are going to be degenerate. So we have one peak. And if we apply electric field, we will have this level split into 3. So by looking at how they split, and we can figure out what is the direction. Now, we discovered that if you look just at the transmission, it's kind of hard, especially if electric field is not homogeneous, as it is obviously for electron beam. But what we started to do now, we had a camera, and it's record the fluorescence from the beam. Now, those of you who may know the history, originally, the coherent superposition for EIT is called the dark state. You may have heard that. Do people know where the word dark came from? It's because if you have the atoms in the state, you have less atom in the excited states, and therefore there is less fluorescence from the state. So if you somehow make your measurement, where you reach the EIT conditions, your sample goes dark or darker. And this is exactly what we're doing here. So now if we have a camera which basically focuses on our laser beam, we see the fluorescence. And then in each of these points, we can trace at which frequencies we have the reduction of fluorescence, and it will tell us where the frequencies are. So this is kind of a joint picture. So this is kind of the signal we record. This is the longitudinal direction of the beam, so we can see along. And this is the frequency of the laser. We're kind of doing this at the same time. And each of the slices is basically the transmission spectrum we can see here. So for example, if we're, okay, this is really hard to aim. Where is it? Yes. Okay, let me for this one try the normal vector. Yes. So for example, if we're here, there is no electric field, so all the peaks are together, so we have a nice peak. We have one on the side where we have like strong electric field from the window, and here we can see kind of the separation of all the different peaks. You can see this to kind of 2 years thing. This is actually electric field from the beam. If you remember your like introductory physics from the wire, electric field basically make this ring. So the cross section is exactly this, what we see here. So by fitting the electric field from here, we can actually reproduce the electron beam distribution. And we also, for these measurements, we measure the fluorescence of the beam as electrons passing by, so no EIT. And these two overlap really, really nicely together. So we believe that we can do that. Now, it's not exactly complete analysis yet, because we don't have information about direction, but I'm going to tell you what we're doing about this. And just again, as a proof, if we move electron beam, we can see that this Batman ears peaks move. And also, if we scale electric beam, we can see that it scales. So it works. OK. So this is with electron beams. And now the nice thing about, you start doing something, and other people say, oh, can you help with our research? So after we started working with electron beams, our colleagues who do plasma physics said, well, can you measure electric field? Because apparently, if you have plasma, normally in plasma, you don't have electric fields in bulk plasma. But on the interfaces between the plasma and conductors, there is a lot of interesting stuff going. Now, talk to the plasma physicists. They will tell you all the exciting thing is going. I don't quite remember all of it. But basically, they really want to know what is happening in this layer. And in general, having a really non-invasive detection of electric fields is something they're very interested in. Because apparently, for the plasma physics, you really just need to put the Legmeyer probe, which is a wire. That's the way they measure it. But it's very, very perturbative. So now we can basically do exactly the same thing, but with the plasma. So we shine the 2 laser beams for our Rydberg EIT. We put the camera. We detect the fluorescence. It will tell you what electric fields are. This is a very much work in progress. And for this particular experiment, we do have like the way to produce the homogeneous electric field. But normally, our kind of probe, we use this wire, which is called Langmuir probe. And if we want to see how electric field behaves, we use this voltage on this probe to do things. So for example, this is, yeah. So this is kind of the same EIT resonances I showed before. There are 2 fine states for the excited states. That's why there is like one line and a second line. But you can see that near the Langmuir probe, so when we're close to the probe, this is we see the splitting between the different levels. So that will tell us the electric field. So we can reproduce the electric field from the probe. And then we can basically create the pictures like this, where we can see how electric field is changing. So this is close to 0, and then it grows. And of course, the green line, that's where we have a laser beam. We cannot see anything outside of it. So we were able to see, for example, that if the laser beam probing fairly far from the probe, when we turn on the plasma, and at this point we're working with the very low density plasmas, we can actually screen the electric fields completely. So you can see that here we have a clear separation near Langmuir probe, as we expect. But as soon as the plasma is on, the resonance is basically, the splitting disappears. Remember, again, the frequency is this way. So the resonances become broader, and that's, again, because it shows the fluctuations in the plasma. What information we get from there, we'll know later. We don't know yet. And what we're already starting to think, for example, is how the plasma would affect the field if you're closer to the probe. So for these experiments, we were able to move the laser beams very close to the probe. And we can see, for example, that this is the recreation of electric field. The filament bias basically gives you more charged particle, the kind of slightly denser plasma. And the more plasma we have, the faster the electric field disappears away from the probe. This is exactly what expected. This is called sheath. Sounds like a name from some sort of medieval evil person or something. But this is what plasma physicists want to know. So if we look without plasma, it's a broader resonance. And then as the plasma becomes denser and denser, it shrinks. And apparently, it will tell us a lot about the plasma when we get there. Again, very much work in progress. So the one thing I said before is that we don't know the direction of electric field, which is kind of a problem. But we're working on this. Remember when I was talking about magnetometry, how we can use the information from different polarization to get information about field. So we're using a similar approach to get this. So for example, here that example, I'm sorry this image is a little busy, but if you first look at the black line, you can see that we have one black peak here and the one black peak here. So that's without electric field. These are where the EIT peaks are when they are not separated. Now, depending if we send in, and in this experiment, electric field is kind of perpendicular to the propagation. So if we direct our electric field to be parallel to the electric, to the polarization of light is parallel to the electric field, then this is a blue line. And you can notice we can see only two peaks over here. But if we send the light which is perpendicular to the electric field, we clearly see the three different lines, and this is from D3 halves. Okay? So why it is so is because depending on the polarization, different excitations will happen. So this is a very much simplified picture. Yeah. This is a kind of simplified picture because, of course, in the real rubidium, we have to include the hyperfine structure, which is not pleasant. But essence you can basically catch here if you use only the total angular momentum J. So for example, you can see that if our polarization and electric field are parallel, and this is our quantization axis, we only have the pi transitions. So you cannot get to the M5 half state. Right? But on the other hand, if you make it perpendicular, then you only excite the sigma plus and sigma minus transition, and you will be kind of preferentially exciting to the sigma M5 half states. So, and this is basically exactly what we see here. As I said, if you want more accuracy, that's a more numerically more complicated because many more levels, but this is kind of a general gist. So now, for example, by rotating the polarizations of light together, we can see at what frequency 5-half disappears, and it will actually tell us. That means that we're perpendicular to or parallel to the electric field direction. And this is what we have right now. So on the images of the top, that experimental images, where we rotate polarizations of two fields, and you can see we create very clear patterns. So one of them, so this one is for M5 halves. This is for M3 halves, this is for M1 half, so these are three things. And here we have kind of a simplified theory where we just include the probabilities of different transitions. We have a theory colleagues who are still working on like full-blown calculations. They claim it's really hard, and I believe them. But you can see that even this kind of simplified model captures the symmetry pretty well, especially for 5 halves and 1 half. 3 half is kind of tricky. It's the hardest one. And if we just cross for the light polarizations to be parallel, to laser be parallel, kind of the diagonals of here, you can see that for 3 different transitions, we actually capture quite a bit the behavior. So that means, again, that if we rotate the laser polarizations and we analyze where we see minima and maxima, we will be able to tell you the azimuthal direction of electric field. So currently, we are very actively working on how to recreate the full direction. Unfortunately, experimentally, we cannot change the direction of the electric field with respect to the laser beam, just because you need the plates. And if you tilt the plates, your laser beam doesn't go through. That's we'll figure something out. This image is literally from like 2 days ago, so But what our students did is that they took the Slagmeyer probe in the big plasma chamber. They didn't have any plasma, so we only used the chamber itself. And then they moved the probe away from the wire. And what we can see is that if the probe is far away, then if we monitor the electric field, it's more or less uniform. And we can see that the brightness of the peaks will show you what the direction of electric field is. But if we approach in the probe, we can really see the strong changes in both kind of phi angle and the longitudinal theta angle. And now we just need to figure out how to extract information from there. Ask me in a few weeks. Hopefully, I will have a better answer for you. But this is our work in progress. Okay. Let me do a little pause. Any questions about this so far? No? OK, good. All right. So let's move to the next thing. So everything I've been talking about up to now, again, they're kind of quantum sensors, but they're kind of classical quantum sensors. We definitely use atomic coherences, but yeah, not so cool quantum. So if we want to move in the next generation of quantum sensors, first question you should ask yourself is why? Like, why do you want to do that? And the main reason why you may want to do this is that if you're limited by the fundamental quantum noise in either your atoms or your photons. So the fundamental, it's called the projection noise or spin noise, is that because if you treat each of your atoms individually, you will have some quantum uncertainty in the direction of your spins. And if you add them all together, that will give you kind of the spin shot noise. And there's nothing you can do about it unless you start creating some sort of a collective states for spins. That's spin squeezing. I'm not an expert in spin squeezing. And even though the spin squeezing is possible with the hot atoms, my very good friend was able to do this experiment. It's really hard. So I'm not sure if it can be really implemented for sort of like practical sensing. So ask cold atom experts about spin squeezing. However, we have a kind of counterpart, because we use an optical atomic sensors, is we have the shot noise of the photon. The same thing is that the photons are independent from each other. And even though we can maybe ensure in the laser that the average flux of photon is constant, since the photons are coming and going together, it's like if you monitor the row of people with about the same kind of throughput, on average, you're going to have the same number of people through the door, but every single moment, sometimes you will have more, sometimes you will have less. So this is kind of the origin for the shot noise. And that's going to limit of how well we can measure with the electric field of light. And therefore, if we do something with the photons, we might be able to reduce this noise. It's not comes for free, so there is a price to pay for this. You will have to design the specific experiment. And honestly, I will, again, if you're staying around for the lectures, we will talk about this more on the third lecture. But I will tell you the dirty secret. Often, one way to reduce the shot noise is to make your probe beam more powerful. The shot noise scales as 1 over square root of the power. So that means that if you can increase the power of your beam, that's the best way to beat the shot noise. You really, the squeezing will help when you cannot no longer increase your power. Because then the only way to go beyond this noise limit will be doing something classical. So that's why there are certain applications for the squeeze light when you have to do it, and it's really advantageous. And let's see if I have this. Yes. So one of them, for example, is LIGO. It's a gravitational wave detector, biggest success for the kind of astrophysics community. They now detected black holes and all the neutron stars and all fun stuff. But there, the detector is engineered to the level where they're really limited basically by the fundamental noise, especially in certain frequency range. And therefore, the only way for them to move forward was to introduce squeezing into interferometer. I think they achieved 3 dB of squeezing, which gives them a factor of 2 for the sensitivity. But because they measure the voltage, factor of 2 increased the voltage, the volume of the university probe, like factor of 8. So they suddenly see way more stars. and way more event. And actually, if you're ever curious, if you go to the LIGO and see the number of detections, it goes like very, very slowly and then very, very rapidly. And guess when the squeezing was introduced? Well, honestly, they introduced a whole bunch of increasement, but I claim squeezing played an important role. So this is a great story to tell. But honestly, LIGO is probably the only one which is unequivocally was helped by squeezing. There are other applications. So for example, people trying to measure some of the absorption resonances, they can really get help from squeezing. I've also heard work where people use the intensity squeezed light to to drop the power limit on optical tweezers, but these are still not quite of mainstream applications. So I would say that the quantum sensors, at least photonic quantum sensors of second generation, are still looking for this killer app to become really, really popular. Okay, so obviously it's a huge topic. So where I'm going to spend remaining time is to maybe talking about how we can use atomic vapor to generate squeezed light, because that's what we are doing. And as with everything, there are pluses and minuses. So one of the big advantages for me, for our group, it is actually a very simple experiment. We work with the two different types of squeezing. For one of them, you literally have a laser, vapor cell, and an analyzer. And you get your squeezing almost for free. Not a lot, though. The other one is slightly more sophisticated, and you need a little more laser power. But it's a great thing. We can have undergraduate students working on that. It's also less expensive. So another one that's more relevant with the atomic sensors. In atomic sensors, you need to be close to the atomic transition. And if you use atoms to generate your squeezing, you kind of automatically in this frequency range. So that's another advantage. However, you can turn it around and say, well, if you generate squeezing only in a very specific frequency, you cannot use it for everything else. So there is not a lot of tunability on that. The squeezing we generate, because it doesn't require cavity, it's multimode. For some applications, we absolutely love it. I'm not going to talk about this, but we can actually use the squeezing for some sort of quantum imaging. But on the other hand, it also means that your squeezing is a mess. So if you really want to know in which shape and mode your squeezing emerge, well, best of luck. My husband right now is working on how you can analyze this, and it's not an easy work. So built-in flexibility, again, this is what we love about atoms, because we understand how atoms work so well. We can really predict or model or adjust the parameters of our system. So this is, I think, is one of the big strengths. And then we can take advantage of resonance enhancement. If we are on resonance, compared to nonlinearity in atoms and, let's say, nonlinear crystal, atoms can be way stronger, which, again, it's typically a good thing. But the bad thing here is that this enhancement comes from all nonlinear processes. And sometimes you have the one you want, and you have the one you don't want. And unfortunately, all of this get enhanced. So ease of integration, that's one of the problems, because, of course, glass cells with the atoms are fine. And for some of the things, they work well. But if you're trying to think about chip scale systems, maybe not. Although there is quite a bit of progress on that. All right, so it's a mixed advertisement for this. But now, how we can generate squeezed light? So there are two ways we can produce squeezing. So one is called the quadrature squeezing. So what it means is that we have a vacuum, and then we have a nonlinearity, and we send the light through the nonlinearity. It can modify the quadratures of this light. The nonlinearity we can use, it's called the polarization self-rotation. So what it means is that if we have a elliptically polarized light, and we send it through the ensemble, of atoms, now we can decompose it into two circular polarizations, and the light shifts create a cross-phase modulation between these two. So basically, intensity of one of the polarization affect the refractive index for another. And what happens at the end is polarization gets rotated. Actually, if you're doing the experiment, sometimes you will see that you send your light through the atomic ensemble, and suddenly your polarization rotates depending on where you are on the transition, which can be annoying. But it's an interesting effect. Now, if you send a linear polarized light, what happens? Oops. If you send in linear polarized light, what happens is the mean field will stay the same because there is no effect. However, the quantum fluctuation in orthogonal polarization will be modified, and you will have a quadrature squeezed vacuum. And you can, the nice thing is that you can really easily to get access to it, because if you put the polarizer after your cell, and you reflect your squeezed vacuum. Or you can also use your pump field as a local oscillator. So we have worked quite a bit on that. Again, we didn't get a lot of squeezing. I think in our lab, the maximum we saw was like 2.5 dB. For this particular system, I don't think people get more than 3 dB, although there was some interesting work a couple months ago when they did some AI improvement, optimization, and I think they claimed they got like 4 dB, and this is already quite impressive. So where we use it, one is for quantum enhanced magnetometry, because if we use kind of Faraday magnetometer, remember how when I show in for the magnetic field detection of electric beam, so when magnetic field creates the rotation of polarization, what limits you in this case is essentially the short noise, how little you can rotate your polarization such that it's comparable to the noise in orthogonal one. And if we use squeezed vacuum, and then we figure out if the right quadrature goes through, we can actually achieve the enhancement of that. Another things which we were doing is that now if you take this squeezed vacuum field and you send it through, let's say, some mask, because if you have the optical loss, it kills your squeezing. That means that if you detect your squeezing afterwards, you can basically see where your squeezing disappeared, and that will tell you where you had the mask. And you can probe it with a very few photons, because squeezed vacuum field have very few average number of photons. So that's another applications for this work. Yeah, I think this is just a magnetometry enhancement. The other type of squeezing we used, and I know there are some people working on this here, is a two-mode squeezing, and it's a very fun system where you basically create the pair of photons at two different frequencies. For us, it's based on the four-wave mixing. And if you look at individually at which fields, they're kind of noisy. But because the photons are created together, these fluctuations are exactly coincide in both of the fields. And in this case, if you look at the intensity difference between the two fields, you can't have the suppression below the kind of short noise limit of individual fields. And this is actually used quite a number of quantum sensors right now for different things. People enhance the magnetometer performance. They perform some weak absorption measurements. And again, what we have done with this is trying to detect like weak absorption resonances. Because, for example, if you look at the intensity difference between the two fields, you have certain short noise. If you introduce a little bit of loss in one of those fields, you actually can gain a lot of sensitivity of measuring the noise between the two fields. Okay. But this is, again, for these measurements, we're really locked to the, we're really locked to rubidium wavelengths. We're very close to rubidium wavelengths. And of course, if you, for example, want to use atomic source for practical telecommunication, you have to switch to the telecom wavelengths. Because that's the light which propagates through the fiber. And there is actually a number of proposals of how people want to create entanglement between the light of the different wavelengths. So the one thing which we can do with rubidium is to look at the ladder system, but this time, instead of with the ladder going all the way to Rydberg atoms, we kind of stay nearby. And if we hit the 4D state, this is actually give us the telecom wavelengths transition. So in this case, we can do the four-wave mixing. Again, the standard four-wave mixing is a double lambda system. But here we have like a diamond system when we have two pump fields. Okay, let me use here. So we have two pump fields, which promotes the atom in the D state. And then we can generate the two fields, bringing them down. And that would be our generated fields. So this is the experiment my recent graduate students complete. So this is the scheme we used. So we used 2 of the lasers for here, and he seeded this transition over here, and this field was generating. So in this case, he found the conditions where we have a 4-way mixing peak. Now, because we now the lifetimes of this transition is lower. This is a lower lifetime than the P states, of course, but it's still like 100th of nanosecond lifetime, so coherence was not that effective. So overall gain was much smaller. But after optimizing everything, he was able to obtain minus 2.6 dB of squeezing, where he was measuring the intensity fluctuations between these 2 different frequency fields. So that just proves, at least proof of principle, that we can use this system if we want to, let's say, create one contrapart which is near the atomic transition. So we can use it for quantum information, or we can use it for sensing. And the other contrapart is in a telecom wavelength. So if we need to send it somewhere and maybe create a network of quantum sensors, we can do that. And of course, 2.6 dB, again, it's not that great. So the question is, can we do better? We were limited by the power of the lasers, which were available, but he did some of the modeling, and he showed that if you kind of continue along the way, we might be able to hit like 6 dB of squeezing with the higher powers. Yep. All right. So I think I talked enough today. So this is our group at William & Mary. And as I said, if anybody's interested in joining us or visiting us, we're very welcome. But my general message today was that, first of all, there is a lot of interesting things we can do with the kind of more traditional quantum sensors. And I think we should explore other options of how we can apply them in the different areas of physics or beyond the physics. And then there is a lot of interesting development we can still do with the quantum 2.0 sensors, although we also want to find where this quantumness would really be necessary to solve some fundamental problem. And so there is a lot of more fundamental questions about that. And again, this is where I would love to talk to any theorists who have crazy ideas about how squeezing co-entanglement can really create something really unusual. All right? Thank you so much for your attention.
Thank you, Irina, for this very impressive talk. Lots of results. So, now, are there any questions? Oh, I'm pretty sure the students have lots of questions, but they are really shy. Okay, so I have lots of questions, for example. And since I have confused and I said that you are working with cold atoms instead of hot, then I do have a question, because I see that every result is very impressive, and but I wondered whether if I go to cold atoms, so would I win, and of course I should lose at some point also. So what would be the advantages and disadvantages for some of those results, at least?
Yes, so the best example I probably can give you is our electric field measurements. So our experiment right now, everything I show was done with the hot atoms. One of the reasons is just because it's much easier to introduce basically a clump of rubidium inside the section of the vacuum system. So you create this vapor and you can make a measurement. However, in this case, we don't really have a control where the atoms are. And also because the atoms are moving, again, as we discussed a little bit today, there is a price you pay for in the reduced signal. So we're actually constructing the next generation of this experiment where we're going to create the cold atom sample. And that will give us two advantages. So first of all, it's expected to provide the much higher sensitivity, because we will be able to we hope we'll be able to keep up the coherence longer. And that means that we can do more interferometric measurements, kind of like a Ramsey approach.
Due to transit time, or what is
well, for right now, we are limited by transit time. But basically, if you can keep your cold atoms somehow, you can keep them much longer. So you can create a Ramsey type of interferometer and measure much smaller changes in the Rydberg state energies. So that's one thing. The second one, of course, is if you can localize your atoms, you can actually choose where they are. So now we have to play a lot of games to understand where electric field, what electric field is in which point in space. If you have your cold atom probe, which is very small, you can literally kind of translate it and probe electric field around the electron beam structure with much better precision. So this is exactly where the cold atoms will have an advantage. Now, if we're talking about integrating this with the actual particle accelerator, I don't think it will be very practical to try to recreate the MOT around, around the vacuum beam. And that's, again, this is the practicality of the hot atoms will certainly play a role.
Mm-hmm. Okay.
I think there is a question.
Yes.
I'm not a student, but I still have a question. I have the right. Thank you. Thank you for the wonderful talk. On this topic, I was wondering how practical it is to implement these kind of measurements in the really in the accelerator with the electron beam, in a sense that there may also be probably interactions between the beam itself and the atoms, ionization, and so how much does it break the measurement, and how much does it maybe influence the property of the beam itself that is used for other experiments?
Right, so excellent question. So let me start from the back. So according to our calculations, because the density of rubidium is very low, its effect on electron beam is kind of negligible. Obviously, again, this is where cold atoms will be good, because if you can put your atoms outside of the beam, then certainly it's not going to be. We don't want the electron to collide with rubidium atoms. It's only going to be accidents when they cross in their own time. But according to calculations, that's a small enough effect. Now, about effect of electrons on the atoms, that's actually a much more interesting thing. And what I discovered when we start talking to the theorists, nobody really knows what is going to be the effect of like relativistic electron passing by Rydberg atoms. Especially if we're thinking about not just ionization, which again, is supposed to be in our parameters is somewhat manageable. So we don't see a lot of drop in rubidium density when we turn on electron beam. But if you have, let's say, atom in the coherent superposition of the darkened ground state, and now you have the electron, relativistic electron zipping by, creating the very strong electric field, but a very short amount of time, how that's going to affect the quantum state, nobody knows. Apparently, nobody looked at that. So we're kind of looking for theorists who want to take this problem. I can warn you that's a really hard problem. We had one group of theorists trying, and then they basically skipped very quickly. But this is actually fundamental things which maybe we can discover. Our electrons are not quite relativistic enough to create these issues yet. But if experiment continues running, maybe we'll discover something really interesting about this.
Done.
Thank you for your wonderful talk. When you were talking about conversion to telecom wavelength, it appeared a question for me. Some groups have demonstrated that besides squeezing, full-wave mixing also generates quantum correlations like entanglement, for instance. So linking this information with telecom conversion, which you talk about, do you know about any work in using this conversion to implement, for instance, quantum information protocols, or even use these correlations to enhance sensitivity of quantum sensors?
So I don't know. So there are certainly several groups which worked on frequency conversion in this case. And yes, it's kind of the same four-wave mixing basic process, but it's a different parameter scale. So for example, we definitely need way higher gain, and we try to figure out how that works. I don't know if anybody really, so the only group, and actually it's a company, I know they produce the telecom single photon source based on this regime. I think when they basically use a heraldine for 780 and then tended. I don't know if anybody moved further than that. But else, I wouldn't claim the complete authority on this. But yeah, so it's certainly possible to convert the photons as well, yes.
Are there any more questions? So if not, let's thank Professor Novikova again. Thank you. And so let's now, for those who are participating in the school, let's take the picture now. So just outside here, okay?